Hello and welcome to this journey towards the uncertain. My name is Fabian Wagner. I'm a PhD student at Stettin University, and this video accompanies a poster titled Asymptotic Extended Uncertainty Principle, whose content is based on the two papers below. We tried to answer the question, how does space-time curvature affect the uncertainty principle? Heisenberg's uncertainty principle shouldn't come as a novelty to you. Yet, based mainly on quantum gravity considerations, people have been modifying it recently. In this context, space-time curvature is supposed to have an effect as well. This is what is called the extended uncertainty principle. The correction is parameterized by the dimensionless beta. LC denotes a curvature length scale. The term asymptotic in this video's title stems from us approximating the metric around P0, which incidentally will be the expectation value of the position operator, employing Riemann normal coordinates xi to second order. Similarly to Heisenberg's uncertainty principle, order derivation takes place in the realm of quantum mechanics in 3 dimensions. Yet the background manifold is understood as a possibly curved 3-dimensional space-like hypersurface of the 4-dimensional spacetime. This construction is, of course, observer-dependent, a behavior which often occurs when quantum mechanics and gravity are combined. It is the observer, whose wordline you can see here, who determines the slicing. What we define to be the position uncertainty will be a diffeomorphism invariant generalization of Heisenberg's slit width. Geodesic balls are defined as having a geodesic distance sigma from their center P0, which is smaller than or equal to their radius ρ, which we choose to represent the position uncertainty. For example, here you can see the deformation of a geodesic ball in green approaching the white horizon as seen from the static observer in the Schwarzschild spacetime. Finally, we want to compute the standard deviation of the momentum operator, which in this setup can be shown to be greater than or equal to the square root of an eigenvalue, say λ1, as a function of ρ. This is the desired uncertainty relation. So, how does spacetime curvature affect the uncertainty principle? At second order, we obtain this result. Beta is negative, that is, positive curvature decreases uncertainty. The role of the squared inverse length scale is played by the Ricci scalar on the hypersurface evaluated at the expected position. This implies that the curvature of spacetime always has to be taken into account for when doing quantum gravity phenomenology, for example, for minimum length scale effects. Speaking of which, by Born reciprocity, the assumption of curvature in momentum space would immediately yield an analogous generalized uncertainty principle. For the time being, bear in mind, the more uncertainty you can tolerate, the more creative you can become.